In this video, we will see the proof of fundamental theorem on finite abelian groups as given in topics in algebra by I.N.Herstein. The statement of the fundamental theorem goes like this: every finite abelian group is the direct product of cyclic groups. So to prove this theorem, we borrow that problem 3 which was explained in the previous video, that if G is a finite abelian group, then G is the direct product of its p-silo subgroups. So we can have our G to be the product of these p-silo subgroups. So here each SI is a pi-silo subgroup of order pi power ni. So to prove the theorem for G, it is enough we prove the theorem for G of order p power n. And we also prove that there exist elements A1 etc. An in G such that every element x in G can be uniquely written as the product of this A1 per alpha 1, A2 per alpha 2 and so on AK per alpha k, so that we can have G to be the direct product of A1, A2 and so on An, where each AI is generated by small ai. So for this we consider A1 in G to be of maximal order, say p power n1, and A1 to be the cyclic group generated by A1. So because A1 is of order p power n1, we have A1 raised to p power n1 to be identity element, named that as equation 1. Now if G equals A1, then the theorem obviously follows. So if not, we shall take an element, say B2 in G, but B2 not in A1. Name that as statement star. Now we consider B2 bar in G mod A1. This is possible because A1 being a subgroup of an abelian group must be normal in G. So the quotient group G mod A1 exists. So in that we shall consider B2 bar, which is actually the image of B2 in G by the canonical homomorphism. And this is assumed to be an element of G mod A1 of maximal order p power n2. So the motivation behind this is, when we consider order of G mod A1, when G is a finite abelian group, we have this order of G by order of A1, and cross multiplying we have order of G to be equal to order of A1 into order of G mod A1. So if G equals A1, then order of G will be equal to order of A1, so there is no need to consider this. But since G is not equal to A1 means, then this one arises. So that motivates us to consider B2 bar in G mod A1 and let it be of maximal order p power n2. So that in turn is interpreted as this: B2 bar p power n2 is A1, and this is again because A1 is the identity element of G mod A1. Now because A1 is an abelian, and that is normal subgroup of G, which is an abelian group, this p power n2 goes inside, so we have this. And using this result xh is equal to h if and only if x belongs to h, we have our B2 per p power n2 belonging to A1. Now since A1 is generated by A1, for some I in Z, we have B2 raised to p power n2 to be A1 per I. Name this as equation 2. Now having got p power n2 and p power n1, we will establish in the first claim that p power n2 divides p power n1. So for that we shall consider order of B2 to be, say, some S, so that B2 per S will be E, and this is automatic. B2 per S A1 is A1. Now because our A1 is normal, this S which is inside will go out, so we have this, and this is already denoted as B2 bar. So B2 bar per S is A1. As for B2 bar is concerned, p power n2 is the least positive integer such that B2 bar per p power n2 is A1. Now here S is any other integer for which B2 bar per S is A1. So using this result 1, in which we have said that least must divide any other, we have p power n2 dividing S, name that as statement A. Now since A1 is of maximal order order p power n1 and B2 per S is E, so this we are discussing in G. So by the third result, where we said that order of any element divides maximal order of an element. So using that we have this. If we name this as statement B from A and B, we can easily conclude that p power n2 divides S and S divides p power n1. So p power n2 dividing p power n1, and this in turn implies that n2 is less than or equal to n1. Now we consider our A2 or rather we will find A2 so that we can find another subgroup A2 generated by this A2. So for that we consider A1 power I whole thing raised to P power N1 minus N2, and because your A1 power I by equation 2 is B2 power P power N2, this step comes, and this on simplification gives you this. And B2 power P power N1 is E for the reason that B2 power S is E and S divides P power N1, so that P power N1 will be multiple of S. So from these two we have B2 power P power N1 to be E. So here what we have is, as for A1 we have A1 power P power N1 to be identity element. This is least and this is any other. So least must divide any other. Using that we have P power N1 dividing this I into P power N1 minus N2. So this in turn implies P power N2 divides I, or rather I is some integer times P power N2 for some j in Z. We have this. Now you consider A1 raised to j P power N2. Then this is nothing but A1 power I, because j into P power N2 is I. And A1 power I is, you have got that to be B2 power P power N2 by equation 2. By equation 2 you have this. So A1 raised to j into P power N2 being this. We collect the same powers so that you have A1 power minus j B2 whole thing raised to P power N2 to be identity element. Now for convenience sake we shall denote this element as some A2, name this equation as phi. So A2 raised to P power N2 is E. So here we notice one thing, that for integer less than P power N2, say that integer is k, we cannot have A2 raised to k to be E. Suppose A2 raised to k is E with k less than P power N2, then A2 power k A1, because this is E, you have that to be equal to A1. Now this xh is equal to h if and only if x belongs to h. Using that result we have A2 per k belonging to A1. But A2 is nothing but A1 raised to minus j B2. So you have this step, and because A1 is generated by A1, small a1, this will be absorbed over here, and we are left with B2 per k belonging to A1. That's a contradiction, because at the beginning we have assumed B2 to be a member of G, but B2 is not a member of A1, which was named as statement star. So we shall take our A2 to be the subgroup generated by A2, small a2. Now we claim that having got A1 and A2, we are going to claim that A1 intersection A2 to be singleton E. Suppose not, then A2 per T, because A2 is generated by small a2, A2 per T will be a member over here, and suppose that member is present in A1. Then what happens, we will see. A2 per T belongs to A1, and this being a member, we have xh is equal to h if and only if x belongs to h. Using that result, we have this step, and here you are replacing your A2 by A1 raised to minus j B2 from 5. So this step that we have, and because G is abelian, we have this T going inside, so we have this, and the A1 being a member of capital A1, this will be absorbed, so you are left with B2 per T A1 equal to A1. Now B2 A1 raised to T is A1. This step is because A1 is normal in G, this T will go outside, so you have this. But this we have denoted as B2 bar, so B2 bar per T is A1. And again, as for B2 bar is concerned, P power N2 is least, and this is any other, so least must divide any other, so using that P power N2 should divide T. So this in turn gives my T to be a multiple of P power N2. So for some integer k, we have T being written as k times P power N2. Now A2 per T, when we consider, we have that to be A2 raised to k into P power N2, and that is A2 raised to P power N2 whole thing raised to k. but this is E, so you have E raised to K and that is E. So A2 per T, which is assumed to be a member of A2 as well as A1, is now an identity element. So the intersection is just singleton E. Now if G equals A1, A2, so we have already got A1 generated by small a1 now, and then we got A2 generated by the small a2. If my G equals A1 and A2, I mean the product A1, A2, then as A1 intersection A2 is singleton E, then G is the direct product of A1 and A2. That is because by the first problem, where we have said that G is the internal direct product of N1 etc. Nn, if and only if G is the product, and then the second one, Ni intersection product Nj, where J not equal to I, the intersection is singleton E, then G is the internal direct product. So using that problem 1, which was explained in the previous video, we have G to be the direct product. So if this is the case, then as N1 is greater than or equal to N2, what is required that we have? So the theorem will follow. If not, then we can find one B3 in G, but B3 not in A1, A2. Now A1 is normal because A1 is a subgroup of G, an abelian group. A1 is normal. Similarly, A2 being a subgroup of G, which is abelian group, so A2 is normal. Whenever A1 and A2 are normal, A1, A2 will exist as a group, subgroup, and even that is also a normal subgroup. So we consider B3 in G, but B3 not in A1, A2. Name that as name that as statement double star. Now we consider B3 double bar, B3 bar, which is a member of G mod A1, A2. And that be the image of B3 of maximal order P power N3. Actually, be the image of B3 bar. Again, the same canonical homomorphism. Here that bar should come of maximal order P power N3. So this is our assumption. Let B3 bar be an element of this of maximal order P power N3. Now we claim that this N3 is less than or equal to N2. So for that, first we consider B3 bar power P power N3, and that being equal to A1, A2. Rewriting this, we have this, and A1, A2 being normal subgroup, this one goes inside, and XH is equal to H if and only if X belongs to H. Using that result, your B3 power P power N3 will belong to A1, A2. Now since B2 bar belongs to G mod A1 is of maximal order P power N2, and B3 A1, which is a member of G mod A1, which is of order P power N2, B3 A1 power P power N2. So if we consider that, that is A1, where from this one comes. See, in result 3, we established this one also, that is, if there is an element A with maximal order and I have some other element, say B with B power M E, then we have B power N to be E. So this part of it that we are using here. So in G mod A1, we have already got B2 bar with maximal order P power N2. Now that you have produced another B3 bar is B3 A1. So we must have for that B3 bar P power N2 should be equal to A1. So it's from this result 3, the second part of it. So that is used here. So we have again A1 normal, so this one goes in, and XH is equal to H if and only if X belongs to H. That is used. So you have B3 power P power N2 belonging to A1. Name that as statement C. Now if this is in A1, naturally B3 power P power N2 into E will be present in A1, A2, or just we write B3 power P power N2 belonging to A1, A2, and this in turn implies that B3 bar the whole bar P power N2 is A1, A2. So as for B3 bar the whole bar, P power N3 is the order, and this is any other integer. So least must divide any other. So you have P power N3 dividing P power N2. So you have from this it's very obvious that n3 can be less than or equal to n2. So this proves our claim 3, that n3 less than or equal to n2. Now again, since B3 per P per N3 belongs to A1, A2, B3 per P per N3 we can rewrite as an element from A1, which being generated by A1 we can write like this, and being generated by small a2, any element here we write it as a2 raised to I2. Name that as equation 6. Now this I1 and I2, they are the new numbers introduced. So we will have a relation between this p raised to n3 and these two numbers like this. P raised to n3 divides I1 and p raised to n3 divides I2. So to prove that, we consider this a1 raised to I1, a2 raised to I2, the whole thing raised to p power n1 minus n3, and this being equal to b3 per p per n3. Just now we had that. So from that we have this. And cancelling out n3, we have b3 raised to p power n1, and that is e, because if I consider a1 or p power n1, we know that already, that is e. So if b3 per k is e, means we have to have our k dividing p power n1, because order of any element divides maximal order of that element. So you have this k dividing this, and hence if you consider b3 raised to p power n1, it will be some integer times k. So that is rewritten in this way, but b3 per k we have taken as e, so you have this to be e, right? So you have b3 raised to p power n1 to be identity element, and this in turn implies this one goes to the other side, so you have this. And obviously this is a member of A1 and this is a member of A2. So directly it belongs to A1, and because of this belongs to A2. And A1 intersection A2 is singleton E known. So A1 raised to this is identity element, and again the same concept, least must divide any other. A1 is order of A1 is p raised to n1, and this is any other integer, so we must have this. This automatically implies that p power n3 divides I1. Now from equation 6, we had b3 raised to p power n3 is a1 raised to I1, a2 raised to I2. So that we are considering, and that is nothing but this, and this on simplification gives me b3 power p power n2 belonging to a1. That's by c, which we have already mentioned. Now we consider this one. Obviously from this you have this to be a member of A1. So x belongs to h means xh should be equal to h. So we have this, and A1 this one is because your A1 is absorbed by capital small a1 is absorbed by this. So you are left with only this. And actually you can take this one inside and then absorb it with this, and then you will be left with a2 raised to I2 p power n2 minus n3 a1, and because a1 is normal, this one will go again out, all that we have. So it's very simple to know how this step comes from here. And a2 now replaced by a1 raised to minus j b2, that's from equation 5. So you have this step, and again this one a1 being absorbed by capital A1, you are left with only this, and because a1 is normal, we shall have this as such, because here b2 a1 we are going to rewrite that as b2 bar. So b2 bar raised to I2 p power n2 minus n3 is a1. So again, p power, as for b2 bar is concerned, p power n2 is the least positive integer, and this is any other integer. So least must divide any other. So we have this step. And from here p power n2 can be cancelled, and this one goes here. So p power n3 divides I2. So this proves our claim 4, that p power n2 divides I1 and this one divides I2. So Now we find A3 so that A3 is generated by this small a3. Now since by claim 1 p power n3 divides I1, p power n3 divides I2, we have I1 to be multiple of p power n3 and multiple of p power n3. This one we denote as j1 and the integer, and this one as j2. Right, now we consider 6. So from that we have a1 raised to j1 p power n3, actually a1 per i1, a2 per i2. So that we rewrite because of this, we have this step, and all p power n3, the powers are grouped, so you have this. You now name the whole lot to be say a3. Then a3 raised to p power n3 is identity element. Now you take your a3 to be the subgroup generated by small a3. As we did in the case of a2, here also we notice that for any k less than p power n3, we cannot have a3 raised to k to be e. Suppose it is the identity element, then this step comes, and from here a3 power k belongs to a1, a2, and a3 is replaced by a3 we have named as this, so yes, substitute that, or rather replace a3 by that, so you have this. And because these two being members of a1, a2, we are left with b3 power k. b3 power k belongs to a1, a2, which contradicts double star, because there we have mentioned that b3 doesn't belong to a1, a2. So now we claim that a3 intersection a1, a2 is singleton E. Suppose this is not true, this is similar to the previous case. So suppose a3 per t, which is a member of this, belongs to a1, a2. So you have this step, and a3 is replaced, so you have this step, and this is absorbed by this, so you have b3 per t alone coming here, and a1, a2 being normal, you have this step, and this is b3 bar, the whole bar, this one, that is of order p power n3, and this is for any other integer t that you have. So p power n3 should divide t, so this in turn gives t to be multiple of p power n3, and therefore a3 raised to t is a3 power m into p power n3. So we have this step, and a3 power p power n3 being e raised to m, we have just e. So you considered a3 power t to be a member of this, and that happens to be e. So the intersection of these two is just a singleton E. So we make use of our first problem, as said earlier, that G will be internal direct product once these two conditions are true. So here we have this condition to be true, and this is also there. So if we assume that G is A1, A2, A3, this is available already, just now we proved. So from this problem we conclude that G is the direct product of A1, A2, A3. So that will prove the theorem. If not, continuing the above process, ultimately being G being finite, it has to end at one stage. So we will arrive at this, that G is the direct product of A1, A2, etc. An, and of course any x in G is written as a unique element from an element from this A1, because that is generated by small a1. It will be of the form say A1 per alpha 1, from here A2 per alpha 2, and so on. So with AI intersection, this product J not equal to I, AJ to be singleton E. So we have G to be the direct product of its cyclic subgroups. That is the end of the proof.